problems there. I choose 95% problems from GATE examination only. I hope the concepts are pretty clear to you people. And I would like to tell you one more thing, friends. Please do problems at your home. Please do practice. You can prefer the last year GATE materials. So it will be very beneficial to you, right? So let's start the second unit, right? The second unit, if I'll talk about the course outline. So BJT and FET will cover in this unit. So let me come to the objective of the unit, and that is to know about the BJT. We'll know how BJT is going to function, and we'll know about the characteristics of the BJT and the biasing, and later we'll see the FET and biasing of the FET. Friends, as I told you earlier, this is the analog circuit in which we'll deal only to the circuits part only. We'll not go inside the device part. Remember, in the diode circuit in the very first unit, if we were talking about the diode, we have seen only circuit. Circuit means how this diode is working. When we'll connect in forward bias, what will happen? When we connect in the reverse bias, what will happen? Like this. So we have deal with the circuit property or the device property. We are not going into the deep of the property. There in the first unit, we did not cover the deep inside of the PN junction or the diode. Okay, what is the working kind of thing. So here also I'll provide the brief introduction about the BJT, about the working of BJT specially. But we'll come out with the circuit parameters like current, beta DC, gain, and so many parameters we'll see in the unit. So we'll see the BJT, we'll take the circuit parts and we'll apply in the network and we'll solve the problems like this. This is all about the BJT. So let me start. The transistor. Friends, what is the transistor mean? See, this is the, I think you people in physics in your 12th standard, you all have seen, I think, rheostat and something. Remember or not? Rheostat, variable resistance. You can change the value of resistance over here, there. Here we have one jockey type of structure like this. This jockey is connected with some circuit kind of like this. This is the battery part over there. So when you will move this jockey part over this rheostat, what will happen? The length of the rheostat or the resistive wire will change. So the resistance of the wire will change, right? The resistance will change, and we can take the different value. If we are having ammeter over here and we are measuring the current in the circuit, we'll get different current at different value of resistance. And it will be obvious because V equal to Ri. You are changing the current, your V is fixed, so definitely you will be having changing current. So this is the electrical part, right? In the old days, we were using the electrical resistive change element, that is the rheostat. There we can change the resistance values, right? Now the same thing replaced in electronics by transistors. Are you getting? In the electronics, the same thing is replaced by transistor. As the name is the name given over here, transistor, resistance is coming over here, right? So transistor is also resistor, but what is the means by trans? We can change this resistance. We can control this resistance. So if you can control the resistance, you can control the voltage and current of the circuit. So in one words, I can say the transistor is nothing but the controlling device. What we'll control later, we'll know about this. So let's start the transistor part itself. Wait a minute. So this is the transistor given over here. The other name of this is BJT, bipolar junction device or transistor, right? So wait a minute, let me take pen over here. So a transistor is basically a silicon and germanium crystal containing three, separate regions. Basically, transistor is like you all people know. If you will take NPN transistor, what you are doing, you are adding two PN junction diodes in this way, right? In this way, you are adding two PN. So, in other words, I can say between two N layers, N-type layers of semiconductor, the P is sandwiched in between them, right? So, how it's going to work in a transistor manner means the resistance will change for this circuit. Actually, friends, we are having four type of biasing over here, how to connect batteries for this NPN particular transistor I'm talking about. But before that, let me introduce these parts. The first part of the transistor we call the emitter. Is it okay? Emitter is highly doped. See, emitter in the NPN transistor, if I'll talk about the NPN transistor, so this emitter region will be highly doped. This is the base region in between collector and emitter. This is the base region and this is the collector. Okay, the collector is given over here. What is the function of the emitter? The function of the emitter is to emit electrons or holes into the base region, but basically into the collector region. The base will be obstacle in between, right? As the name suggests, the emitter is to work as an emitter. It has to emit the electrons or holes into the circuit or into the device or into the collector part, right? What is the function of collector? The function of the collector by the name given itself, to collect the electrons or holes coming from the emitters, right? It has to collect. So the doping of the collector is moderate. Why moderate? Because number of couple of holes and electrons are coming from the emitter part. So we have to restore or store them over here, collector. So we'll be having a good area over here. So the collector part of the BJT transistor is, the area of the collector is high than emitter. What about the base? This is the base region. In between collector and emitter, we call it the base region. This is the moderately doped. This is less doped. See, in the base region, the doping is very less and this is very thin part, okay? So, what is going to the system? See, friends, if you will connect this device to some outer circuit, the current will come into the picture, right? Or into the circuit, the current will flow. Definitely, this current will pass this circuit and will come out also. But if here the current is coming IC, here the current is not IC, it will be, at the input stage, if your current is IE, at the output stage you'll get the IC current. But this is the fully controlled current. What I'm saying is, how you are going to control it? What is the difference between simple resistance and this transistor? Here also the current is flowing into the resistive element due to this battery, and at the output you are getting the same current. The same current is going into the element, and the output stage I'm getting the same current. But here I'm not getting the same current. I can control this current by this reason. This is the base reason, right? And base is responsible to controlling the device or controlling the transistor. The whole electronics base is how to control the systems or elements. If you are able to control the elements, then this is the part of electronics, or this is the part of electronics intelligence, okay? So we should be able to control the device. So similarly, the same thing is going to there in the BJT also. In the BJT bijunction device, what I'm saying is the emitter will emit the holes or electrons into the circuit. The collector will collect it, and due to base, or with the help of base, will control the upcoming of the current from emitter, right? Come to the theory part. A transistor is basically a silicon or germanium crystal containing three separate regions. It can be either NPN or PNP. You can see over here. The middle region is called the base, and the outer two regions are called emitter and collector. The outer layer, although they are of same, but their functions can't be changed. the function of the emitter to emit the electrons or holes into the circuit, and the function of collector is to collect them, right? They have different physical and electrical properties. The physical properties I told you earlier, that emitter is moderate in size, this is large in size, and this is thin, very thin, right? Well, we'll come to the, wait a minute. So in most transistor, emitter is heavily doped. And why emitter is heavily doped? Because emitter has to emit the electrons or holes into the circuit, right? Its job is to emit or inject electrons into the base. Okay? It will inject electrons into the base. The electrons will come to the collector region by passing this or crossing the base region, right? So these bases are lightly doped and very thin. The base is very thin and lightly doped. It passes most of the emitter injected electrons on the collector. Okay, if 100 numbers of electrons are emitted by emitter, so it will go to the base region, and like 98 and 90, 97 or 98 electrons will come out. Okay. The doping level of the collector is intermediate between the heavy doping of emitter and the light doping of the base. Why? I told you earlier, because it has to collect the electrons which are coming from the emitter region. So if the area of the collector will be less, so there will be heat problem, right? The collector is so named because it collects electrons from base. The collector is the largest of the three regions. It must dissipate more heat than the emitter. It must dissipate more heat than the emitter or base. I hope this point is clear to you. The transistor has two junctions. Here we are having two junctions because we are adding two PN junctions, right? If you are consider this N, P, N, so this N and P will make one junction over here. I can say this emitter base junction. And in the second part, the P, N are connected. So collector and base, they are having their own junction over here. So this is junction 1, junction 2. This is the emitter base and this is the collector base. So the transistor has two junctions, one between emitter and the base and other between the base and the collector. Because of this, the transistor is similar to two diodes, one emitter diode and other is collector base diode. I hope this is clear to you. Okay, let's come to the BJT symbol. The symbol of NPN and the PNP transistor is shown in the figure. See, how is it? This is the symbol, right? This is the always emitter part. Is it okay? Sorry, this is the collector over here, given over here. Okay, let me check it. For me, this is the collector region, this is emitter region, and this is base region, right? So, why this figure is looking like this? See, what is going on? You are applying the current into the emitter. The current is coming to the collector, but you are controlling by base, right? This is kind of. So, for the BJT, if this arrow, you can encircle it. If this arrow is coming out, so this is NPN transistor. If this arrow is, going inside, so I'll call it PNP transistor. Okay. So we'll see about this. Into this circuit, suppose this is the base current IB and the resistance between collector and emitter is RCE. We have seen in the figure also. In the figure, this is E, base and collector, right? This is nothing but one kind of resistance or not. Control the resistance. Earlier I told you this is rheostat kind of thing. In the electronics way, you are controlling the resistance of it, right? So what is my point? My point is the resistance between emitter and the collector is RCE, denoted like over here. So in the outer circuit, if I'll talk about, the current IC will flow, right? This is kind of thing. So who is the controlling part? The base is the controlling part. If IB will be 0, the circuit will be in cutoff. There will be nothing. Right? Why? Later we'll discuss about this. Come to the configurations. And before this, we have to check one more concept. Let me take this concept of the phrase page. See friends, we have seen the symbol of transistor, right? Here I'm drawing it again. So this is the collector part, this is emitter part, and this is base part, okay? This is the symbol of transistor, and the actual transistor is like this, 3-layer device and 3-terminal device, right? Like this. Okay, this is the emitter, this is base, and this is collector. Now the point is, see, what you are going to do if you will study this, you are saying that, or you will get that in this circuit you are having two types of diode, or two diodes. See, this is the NP diode, so the diode is like this. Is it okay? This is another diode. It means you are connected two diodes in this way. This is this type of situation, right? And in between them, see, this is the two diodes you are connected, and you are controlling this part, right? So from base to collector you are having one diode, and this is in this circuit the base is referenced, right? So from base to collector you have, for NPN if I'll talk about, the diode is like this. The base is P type, collector is N type. So definitely the diode direction, the symbol of the diode will be look like this only, right? And in between base and emitter also you have one diode, base emitter diode. Like this the circuit is. Is it okay? So friends, based on this, we are having the three reasons of working of this transistor, right? And the voltage across this I can call the VBC. Can I? Voltage across this I can call it VBE. Is it okay? So two diodes in between base and collector, one, and one is in between base and emitter. Okay. So friends, as I told you, we have to see the operating reasons. Later we'll discuss in brief, but wait a minute, let me erase it. So friends, we are having two junctions, okay? One is emitter base junction, and another one is collector base junction, collector and base junction. The base is the reference or the common part in between them. We'll consider the emitter base and collector base, okay? So this is the emitter base and this is the collector base. Now if you biasing means you have to apply the outer energy source to the circuit. If you will bias this circuit, emitter base junction is in forward bias, and the collector, or let me start from reverse bias, both. If both are in reverse bias, this reverse bias and this will be reverse bias, what will happen, you know? There will be no current in the circuit. If this is the transistor NPN. Now what you are going to do is, emitter base junction, you are making it negatively like this. And to collector base junction, again you are doing negative bias. It's looking like this. So the depletion in this is the fully reverse bias circuit. In the reverse bias circuit, there will be I equal to 0. We have seen in the diode circuit, right? Depletion layer will enlarge in that theory and all, okay? But I'm not interested to tell you this again. What I'm saying is, in the reverse bias, the current in the circuit will be 0. So this region we call the cutoff region. The transistor is in cutoff. So this is working like a switch. If you applied reverse bias on the both junctions, you are getting 0 output. So this is like working like a switch. Okay. So suppose you are adding somewhere a transistor, you are using the transistor, and due to this transistor you have the current flow in the circuit. But now you want to, suppose some device is working because of this current. Now you want to off this device. So what you will do, you will off the switch, right? So you will change the polarity or you will change the emitter base junction biasing and collector base biasing, suddenly this will be off if you will do them reverse bias, right? So it's looking like or working like switch. Is it okay? Now what if you will do it forward bias both? In this case, the transistor will work as saturation in the saturation region. There will be a constant current in this case. This is the saturation region. In digital, if we'll talk about, so this is the cutoff region and this is, I'm sorry for this, and this is saturation region kind of thing. In saturation, the value will be fixed, and the cutoff region, the value will be 0 kind of thing. Is it okay? I hope it's clear to you. Now, if I'll come to the very important active region, this is the very important because in this region only we are amplifying. So transistor is also used to amplify the input, okay? So in the active region, the emitter and base should be forward bias and this should be in reverse bias. Then only I can, use it like amplifier. Later we'll discuss about this. And what if you are changing this, like this will be in reverse bias and this will be in forward bias. In this case, this will be reverse active. Reverse active means all action will complete it now on the reverse way. Is it okay? So this is the brief idea of the circuit of BJT. Later we'll discuss it. Now come to the next part. And this is the common base, common collector and common emitter configuration. What is the common collector, base and emitter? See friends, here I have the emitter, here I have the base, here I have the collector. Now we have to apply outer energy source to this, right? So suppose we are applying like this. Suppose we are applying like this. In this way you are applying this. So if you observe this carefully, you will find that this base region is common in between them. The base region is common for these two energy sources, V2 and V1. Is it okay? So this is the common base. If you will draw it according, so to this configuration, I'll call the common base, right? You can see over here. But what if you will common the collector? Let me show over here. This is the collector part of the BJT. Now the collector will be common in between them, right? Now you will apply the battery like this. This is the base collector junction and this is the emitter collector. So here the collector is common, right? So this is VEC, this is VBC, okay? So this is the collector, so I'll call it common collector. Similarly, if you'll common the emitter part of the BJT, it will be common emitter, okay? Now we'll see details about common emitter configuration. The common emitter configuration of BJT is shown in figure, right? So friends, this is the NPN transistor. Why? Because this arrow is coming out. This is the PNP transistor because this arrow is coming in. This part of the transistor I'll call the collector, this part of the transistor I'll call emitter, and this part is base. Similarly, the same thing is over here also. This is B, collector and emitter. Now in this, if you'll observe, this is the common emitter. Common emitter, how the common emitter? See, the emitter is directly grounded over here. At the base, you are applying the input. Wait a minute, let me erase some part. At the base, you are applying some input, okay. At the collector part, this is the collector part, you are taking some output. So, if the base is input and collector is output, so obviously the emitter will be common or not? Or you can see this circuit in this way. Let me erase some part. Wait a minute. So to this circuit, see, you applied V in over here. V in, and this is the grounded. So this is the ground. You can join the ground. Here you are taking V0, okay, V0, and reference is ground. So this is the common emitter, right? Similarly, this one also the common emitter, we are showing two NPN and PNP transistors. So in common emitter configuration, the emitter is made common to the input and output. It is also referred to as grounded emitter configuration because we grounded the emitter over here. It is most commonly used configuration, and this is very important. Okay. In this, base current and output voltage are taken as independent parameters and input voltage and output currents as dependent parameters. Okay. So let me draw the common emitter symbol over here. This is the emitter part, base and collector, right? Collector, base and emitter part. Okay. Now VBE, the voltage between base and emitter, VBE, sorry, this is minus, is the function of IB. Definitely it will be function of IB and VCE. Here is the VCE. Okay. So this VBE is the function of VCE and IB. Sorry. Yeah, IB current in the base region. Later we'll know. And if we'll talk about the IC, this is the output current, right? Because you are taking output at the collector junction. So definitely it will be your output. Okay. And this collector output current IC is the function of IB and VCE. Okay. So output characteristics of CE is given over here. Okay. Let me change the color, then we'll discuss about it. Friends, this is the cutoff region given over here. In the cutoff region, the IB is 0. If you remember earlier we discussed, if IB in the capacitor, the transistor is 0, then transistor will work in cutoff region. This will be fully cut off, right? So you can see over here. Okay. And this is the active region given over here, right? So by this circuit, I'll show you these characteristics. Before that, let me draw this circuit again, so it will be clear to understand, right? I'm taking the symbol again. This is emitter, this is collector part, and this is base part. Okay. As I told you earlier, in between, this is the collector over here. Okay. This is the collector. Okay. In the collector and emitter, I have resistance RCE, or you can take it EC, CE. No problem at all. Right. This is the bidirectional and passive device. In the collector, in this, you have IC. This is the outer CE. If I'll take resistance over here, let's give the name RB. Here, VB, okay, fine, and this is grounded, common emitter. Here, VCC, and now you are having two mesh over here. This is the input mesh, then this is the output. Or in other words, I can say this is the input loop and this is the output loop. So, what this IB is going to do in the circuit, or what transistor is going to do? As I told you earlier, in the starting, transistor is nothing but the variable resistance device. We are changing the resistance of transistor with the help of this current IB, right? N, P, N. This is acting like resistor, but this resistor is the fully controlled because of this base reason. So because of this base current, we are going to control it, right? So if the IB is 0, so resistance between collector and emitter is infinity. The situation is like this is IB and this is RCE, and here IC is given. If IB is 0, resistance between collector and emitter is infinity. Okay, so can I say this resistance between collector and emitter is going to control by IB? Okay, I'll tell you it. So IC in this case will be 0. But as you increasing the IB, suppose let's take it 1 micro, there will be some resistance. Let's take resistance value 1K. You are having some current IC over here. So as you increasing this beta or base current, your resistance is going to decrease 500k in something. Not in this manner, but it going to decrease. What it means, when you increase the IB, your current will decrease. Sorry, the resistance will decrease. When resistance will decrease, your current will increase. Is increase in VCE. Is it okay? This is the understanding of this output characteristics. Now you will understand it. When IB is 0, the entire circuit in cutoff region. Cutoff region means there is no current. IC is 0. But as you increase the IB, see, this is the way in which IB is going to increase. Here IB is something, here is IB is something. So here IB is greater than to this one. If this is IB2, this is IB1. So IB2 is greater than IB1. So in this vertically direction, IB is going to increase. When IB is increase, I told you that IC will also increase. Why? Because RC is going to reduce. If we are applying IB over here, you are going to apply. Your IC will increase because your resistance is going to decrease. So when IB is equal to 0, that was the cutoff region, okay? And at one time we'll see at particular value of IB, there will be 0 resistance in between collector and emitter. That condition I'll call the saturation. That condition will be saturation. In the saturation region, the resistance between collector and emitter is 0 or near to 0. So in this graph, if you will see this saturation region, why I'm showing this saturation region? Because here the resistance value is very, very low. See, for the small increment of VCE, current is increasing like anything. So in this case, current is increasing in infinite way, like very large value. So resistance is V by I. Is it okay? I is very large. Resistance will very low. Okay. So this is the saturation region. And this is the active region. In the active region, the collector current is constant. So that's why in the common emitter or in any transistor, the active region is very important. Okay. Because saturation region and cutoff region, these two regions we are using for switching application only. Switching application only. You want to cut off some device from the circuit, you can apply the cutoff biasing of the transistor. So at the output, you'll be having 0 current in your hand. Is it okay? If you want to turn on any device, you can apply the saturation region in the BJT. Immediately, you'll get the output. So these two regions are switching regions. But the active region in which the collector current become constant is the region in which we are amplifying. We are amplifying over here. Okay. So the active region is very important. So by this characteristics, we can easily come out with 3 things, and that is the transistor works in 3 regions, and that is mainly cutoff. The second one is saturation. And the third one is active region. These are the 3 regions of operations. Okay. So let's come to the theory part of this output characteristics. The output characteristic is the curve between VCE and IC. Please remember. VCE, the voltage between collector and emitter, and collector current. Because this is nothing but the voltage at output or output circuit, right? Or the voltage we are controlling, right? For various value of IB, for fixed value of IB, and is shown in the figure. See, for the various value of IB, we have shown here the output characteristics of the transistor. Now for fixed value of IB, IC is not varying much and dependent on VC, but slope are greater than CE characteristics. Forget about this. The output characteristics can again be divided into three parts. This is the important part, that is the active region, saturation region and cutoff region. Right? Now we have to discuss some, okay, let me draw the circuit, then we'll discuss some current part of the transistor. This is the NPN connected over here. This is base. Okay. In the NPN transistor, the current is outgoing. Okay. Emitter current. IB is incoming and IC is also incoming. So for any transistor, the relation between these three currents is like IE is equal to IC plus IB. Who is responsible for current in the circuit? Obviously emitter. So the producer current will be equal to the delivered current. Is it okay? So IE will be equal to IC plus IB. There is one large signal current gain also. We call it the beta DC in the transistor, and the beta DC is given by the ratio of IC by IB. Is defined as the transfer ratio or large signal ratio or current gain, that is beta DC. So this beta DC is introduced here. Beta is IC by IB. Is it okay to you people? This is the output current. This is the input base current. So why this is gain? This is the output. This is the input. So this beta will be gain or not. And typical value of the beta is 49 to 99. This is the typical value of the beta or in general values, right? Output by input. Similarly, we are having another parameter, that is alpha, and alpha is IC divided by IE. Okay, let me take it on the phrase page so it will be clear to you. I'm considering NPN region. Okay. This is emitter part, collector part and base part. If you are considering N, so you'll be having outer current from the emitter. The current will come out from the emitter like this. Okay. The current will enter into the base part and current will enter into the collector part. So if you will see this, the current IE equal to IB plus IC. Is it okay? In the transistor, this base current is very less. This is the very less current. Alright. So in the transistor, I is nearly equal to IC. This is 1.1. This is the equation A. Let's take it. And from this equation, we are having the point I equal to nearly equal to IC. Okay. Because IB is very low or very less. See, if in general we are getting the IE and IC in milliamperes. But if I'll talk about IB in general we are getting in microamperes. So IB is very less current, we can neglect it, right? In the previous slide, we have seen the beta DC. This is the current gain and DC gain. So this current gain is given by IC by IE. Is it, sorry, IB. This is IB. So this is microcurrent, this is millicurrent, beta DC is very high. Okay. Similarly, I'm getting alpha, and alpha is given by IC by IE. So IC is, slightly less than IE, so alpha will be less than 1 always. Is it okay? This is also type of current gain, but here we are not considering IE as an input. As an input parameter, we are considering IB, or if you want to amplify through transistor, you have to choose the base parameter as the input parameter. Okay, or you have to amplify the IE B. Is it okay? So there is another formula, and that is IE equal to 1 plus beta of IB. IE will be 1 plus beta times of IB, and by this formula IC will be beta times of IB. Is it okay to you people? This is let's give it 2 and let's give it 3. IE will be 1 plus beta times of IB, and IC will be beta IB. So if you'll be having relation between alpha and beta, so you need IC and IE, just divide these two. So IC by IE, when you will divide these things, you are getting alpha, and alpha is beta divided by beta plus 1. So this is the relation between alpha and beta. Is it okay? So these are some parameters or some equations related to the transistor. Now the formula, this one is very important. IE is nearly equal to IC, and these two formulas or equations are very important. Okay, you have to remember this. So in the last slide we discussed about regions of operation: active region, cutoff region, alright, and saturation region. The transistor operates in these three regions only, and in which this active is very famous or useful because it is used in amplification, and these two are used for switching. Okay. So friends, these three things are very important. We have to select the transistor, or we have to know about the transistor, that the transistor in working at particular time in which region. Okay, while solving the questions or problems, basically from gate problems, we are getting this concept frequently, and the concept is what will be the output or input parameters and something. I'll introduce with some problem for this same reason, but our heading is to find out region of operation. Okay, region of operation I'm talking about. See friends, what is the problem and why we have to check this? I'll tell you. Let me consider one problem over here. The problem is given this is grounded. Here I have 100K like this, and this is 2.7. Okay, and this is 1K and 5 volt. Now the question is, find out the region of operation. In which region this transistor is working? What is the region of operation? We'll check 3 points: whether it's working in active region, whether it's working in saturation region, or in cutoff region. One by one we'll check all these three. If we could find this, any of this, we can say the condition of any of this, we can say the transistor is working in particular region. The condition for saturation is what? The condition for saturation is RCE will be 0 or VCE will be 0 or not. If you remember that particular symbol like this, over here I have RCE, across here also I have VCE, kind of. In the saturation region the RCE was very low, so in this case VCE obviously will be low. So this is the condition for saturation. What about cutoff? For the cutoff, the standard condition is IB should be 0. What about active? The active condition I'll introduce over here. See, they are saying find out the region of operation. Though this system is not working in the cutoff because I have definitely IB, because you applied some energy source over here. And between base and emitter I have VBE, and VBE is the always 0.7 for transistor. Okay, base emitter region. This is the, you can understand like barrier potential kind of thing in the diode. We have seen barrier potential or not. For the silicon diode we are having 0.7 and 0.3 for the germanium diode. This is the minimum voltage required to operate the diode. Similarly, this is the minimum voltage required to operate transistor given by VBE 0.7 volt. Is it okay to you? So definitely this is not in cutoff region. Definitely this is not in cutoff region. So how we'll check now the saturation and active? We are having standard procedure for that. Just follow me. You will get the idea. Okay. So first I'll tell you what is the procedure. Then we'll apply the procedure into this given problem. Okay. So the procedure is the very first point. Let me change the, okay. So the steps are steps to find out the region of operation. The first step is find IC saturation. Find IC saturation first. This is your first step. What is IC saturation? The saturation, see, remember one thing, the saturation current is the highest current in the transistor. Okay, the saturation is the maximum current, I can say this is the max current in any transistor. Saturation current. IC saturation, in the saturation we have discussed the VCE should be 0. VCE, where is the C? This is C, this is E. In between this there should be one short circuit because the voltage is 0. If this is short circuit, can you find out this IC? Yes, you can find out. So now suppose you have found out the IC saturation. Now in the second reason you have to find IC active. Find IC active. IC active is totally depend on IB or not, tell me. Who is controlling IC? IB is controlling IC. So the active IC or the collector active current is, we have seen in the formula, the IC is beta IB. Is it okay or not? So by this procedure to, in the saturation by applying VC equal to 0, you'll be find IC. Now secondly you have to find the I active. Your I active will be, IC is nothing but beta IB. Now you need input parameter, that is IB. So you will apply the KVL over the input. You will multiply with beta. For this circuit beta is given 100. You will multiply that IB with beta, you will get IC. You are getting some IC over here. This is IC active. You are getting something. Now in the third stage you will check if IC active, the condition third is, if you find that IC active is something is greater than IC saturation. IC saturation. Suppose the condition is IC active is greater than IC saturation. So this is not possible. Why not possible? Because the saturation current is the max current in any transistor. So this condition is faulty condition. So what it indicates? It indicates that your BJT is working in saturation region. Saturation region. Your IC active is exceeding IC saturation, I max saturation. It means definitely the upper point of your BJT is saturation only. Now what if IC active current is lower than IC saturation? Lower than saturation. Saturation current is something that is the max current. Now your active current is less than the max current. What it means? It means that yes, your transistor is working in active region. Right? When IC will exit from the saturation, means it's a default. No current can exit the IC saturation. So if this type of condition will come, the circuit will work in the saturation region itself. Is it okay to you? Now we'll check this circuit. Okay, I'll draw it again for you and we'll check it. The condition or the question is given the 5 volt VCC, here 1K, this is 1K, okay. The emitter region is grounded over here. In the base region, the 100K ohm, 100K resistor connected with 2.7 volt battery, and this is 100 given over here, this is beta. I have to assume this voltage drop VBE always for any transistor 0.7 volt. Okay. According to my procedure, first I have to find out IC saturation. How to find out IC saturation? By doing VCE 0. VCE 0, you have to do VCE 0. Means you have to short these two terminals, collector and emitter. Now you have this outer circuit. Can you find out this current for me? Yes. This IC. IC saturation is the max current. It can be maximum than IC active, no problem at all. And for this circuit, the 5 milliampere is greater than IC. The IC is, tell me, 2 milliampere. So your circuit is working in active region. Your circuit is working in the active region. So this is the procedure how to find out the 3 regions. Okay. So this is all about today's class. This was little bit boring because this is theory part. From the next video onwards, we'll deal with the problems only. I'll illustrate whatever I want to deliver in the form of problems only. Okay, friends. So we'll meet in the next. Till then, take care and bye.